Okay. And here, if you ask what is probability of states in my information set, then my probability, updated probability, has to be proportional to my prior belief. Right? So in this example, again, coming back to this example, this guy knows either this one and this one is true state. Then if you ask what is my updated probability for each state, then we have to have 3 times, this probability have to be 3 times of this probability, because my prior here 1/2 is 3 times of 1/6. So which means that my updated probability has to be proportional to my prior belief. Okay? And however, probability have to be, the sum of all probabilities has to be equal to 1. So here we have denominator here just to make sure that the sum of all probabilities is equal to 1. Okay? So applying this calculation here, formula here mechanically, then if you have asked me what is agent 1's belief about for TU, conditional on true state is TD. So here we have true state, and this is our state we are asking about. And this is first, for denominator, you have to be add up all prior of stage in the same partition. So you have 1/2 plus 1/6 as the denominator, and as a numerator you have omega, you have prior over TU, which is actually equals to 1/2. Okay? And if you ask what is that my prior for TD for the same case, then we have same denominator, but my numerator is now my prior for the state TD, which is 1/6. Okay? And if you calculate it, actually denominator is what? Denominator is 2/3, 1/2, which is equally 3/4, and this is 1/2. Okay? So here, we have to have denominator equals to this thing, just to make sure that this probability plus this probability is equal to 1. Okay? Any question? I think if you have any difficulty following my calculation here, it is probably because you forget what you have learned about Bayesian updating rule before. And that's okay. I mean, that's pretty absolutely natural. All of us forget. So, but it's okay, totally okay, even if you don't remember anything about what you have learned before. But then you have to review some econometrics rule or statistics. Or I also found that actually Wikipedia page is also very helpful. And that I think it's probably better to review these things first, conditional probability, Bayesian rule, etc. Then after you look at the slide again, after you review everything, actually what I have in my slide is absolutely trivial. Okay. Okay. No. I see. So here we assume true state is TU, right? But actually, okay, so you know what? Actually, maybe I have to put TU here, of course. But I'm sorry. So first of all, there was my mistake. But the thing is that even if you replace TD with TU, nothing will change, right? Because agent 1 cannot tear apart TD and TU. So we still have exactly the same equation. Okay, so one last thing is, here is some additional terminology I'm going to use, which is actually standard language in probability theory. So let's say two events A and B. We say two events A and B are statistically independent if this is true and this is true. What does it mean? Here we have conditional probability, right? So here P of A bar B, that is what is probability if I know that B is true, right? But here, the condition here is that that probability is equal to PA, which means that knowing B is true does not really change anything, right? So knowing B is true does not change anything about my probability. And the same thing, you can read the second condition in similar way. Knowing whether A is true or not, that does not tell anything about my probability. That does not change anything about my probability for B. Okay? So then, any information about A is not relevant for predicting any inference about B, and any information about A is also not really relevant for any inference about A. So then we can say A and B are statistically dependent. Okay? So in this example, you can say actually, in this example, you can say here, applying the same language, you can say that election outcome and stock market outcome are not statistically independent, right? Because before I observe independent. Okay, so let's to check that. Let's check what is probability of stock market T. U. So this means that I didn't really introduce this notation, but rho 1 of U, that is my probability that stock market goes up before observe anything. Okay? So what is this probability? So stock market goes up if true state is either this one or this one. Right? And this probability is 1/2. This we have 1/6. So this probability is simply sum of two fractions, 1/2 and 1/6, which is equal to what? 4/6, which is 2/3. Okay, so this is my prior for stock market going up before I observe anything. Agent 1. By I mean agent 1. So, and if you calculate for the stock market going down, so here we have 2/3, so this probability has to be equal to 1 minus 2/3, which is 1/3. Okay? So this is my belief, agent 1's belief before he or she observe anything about election outcome. But you can see this probability is different from my prior, right? So before I observe anything, I believe market outcome is good with probability 2/3. But after I observe Trump wins, I update my belief. So now I believe market outcome is good with probability 3/4, 3/4, 3/4. Okay, so which means that actually my observing the election outcome is relevant in my prediction or inference about the stock market, because my observation changes my belief about stock market. Okay. Okay, so actually I kind of, wrote down exactly kind of similar thing by last slide. Okay, any question? Okay, then. Okay, everything. And now the next step is we have to incorporate what we have discussed so far into the context of the game theory. Okay, so that's our next step. And we begin with the static game first. So by static game, what I mean is that there is no really dynamic. All players choose their actions simultaneously, and that's like in normal game. So here, in the title, I have static game. Okay, static game means normal form game. All actions are taken simultaneously, and I have incomplete information. So incomplete information is kind of almost synonym of asymmetric information. Okay, so I have a little bit of incomplete information about what you have observed, for example. Okay, and static game with incomplete information. For historical reason, we call these games Bayesian games. Okay, so I don't really think you are interested in historical reason why it is called Bayesian game, but just in case, okay, so actually in 50s and 60s, there was a lot of debate about how to model uncertainty and asymmetric information. And the thing I just presented to you, the model of asymmetric information, I presented to you, that was firstly proposed by Hassani, one of Nobel Prize winner, many years ago. He proposed the exact way I presented to model asymmetric information. And as you already saw, Bayesian updating rule plays an important role, right? In our discussion of how to model asymmetric information and uncertainty. So, because Bayesian updating plays so important role, people call the game with uncertainty being modeled by the way I just presented. People call those kind of games, class of those kind of games, Bayesian games. Okay? So that's the reason, historical reason why we call these games Bayesian games. Okay, so here this is one example how to incorporate asymmetric information or incomplete information into our game theoretic context. So here we have two games. So both of them are a version of coordination game. So let's say we have two players, player 1 and player 2. So they are seeing each other, so they are dating. Okay, so and they have to choose where to go, either football game or concert. Okay, and if they go to the same place together, then they have positive payoff. And if they go to different places, and their payoffs are 0. Okay. However, player 2 does not know exactly which kind of preference that player 1 has. So to put another way, so let me put it this way. So player 1 is either concert type or football type. And if player 1 is concert type, then the left table, that is the payoff of player 1. In the case that player 1 is concert type. Here you can see, player 1, if focusing on player 1, this guy like to go to the same place with player 2, but if he can choose, he or she would like to go to the concert instead of football game. Payoff from going concert together is 2, but payoff from going to football game together is 1. But if player 1 is football guy type, then this is the payoff. The right-hand side table is player 1's payoff. So as he prefers going to football game together, or she, yeah. And if you think about, look, and you can also find out that in both cases, there is no real difference in terms of in player 2's payoff, right? So this is the situation we would like to model and solve. What is the equilibrium for this case? So player 1 and player 1 is either football guy or concert guy, or football type or concert type, and player 1 of course knows that, which is about player 1 knows whether he or she is football guy or concert guy, because it is all about this guy's preferences, and this guy has to know what is his or her preference, of course. But player 2 does not tell exactly what is player 1's type. Okay? And if player 1 is football guy, then the right-hand side one is the game they will actually play, right? But if player 1 is concert guy, then the left-hand side is the game they will actually play together. And player 2 does not know which one is the true game they will play together. Okay, then you can use our framework or state space and this kind of all stuff to model this thing. So let's say prior for this case is 1/2, and prior for this other case is 1/2. So they are equally right. Then in this case, the set of relevant state space is theta C and theta F. Theta C means that player 1 is concert guy, and theta F means player 1 is football guy. Okay? And you say that, let's say that, okay, so and we said that two cases are equally likely. That means that they have this prior. So they assign exactly the same probability for both possible states, both of them. So they have common prior. Okay? However, so there is difference between two guys now. Player 1 can say whether this one is true or this one is true, which means that all of this guy's information set only has single state, which means that this guy can exactly say whether I am football guy or concert guy. So however, if you look at the information sets of player 2, there is only one information set, and in this information set, we have both theta C and theta F, which means that player 2 cannot tell apart whether this is true state is theta C or theta F. Okay, so if you write down everything this way, that exactly describes our story. Player 1 knows his or her own type, while player 2 does not. Okay, so here is the next slide. The second slide is about exactly the same situation, but slightly different interpretation. So actually, it's not really different interpretation, but it's just a matter of how I present. But sometimes, this alternative mode of presentation is easier to understand everything. So in the previous slide, I say that there are two players, player 1 and player 2, and player 1's type is uncertain to player 2, right? But alternatively, you can say that you can describe exactly the same situation in slightly different way. Let's say there are three players. Player theta C, player theta F, and player 2. Okay? And player 2 is matched either theta C, player theta C, or player theta F. Okay? However, player 2 does not exactly know who is my opponent, whether it is theta C or theta F. Okay? And then anyway, player 2 will play the game together with my own partner without knowing whether this is player theta C or theta F. Okay? So then, then we have, so sometimes this kind of alternative interpretation saying that player 1 of different types are actually different players. So this kind of alternative way to describe everything, but sometimes it is really useful. Okay, but actually, two descriptions are exactly describing exactly the same situation, right? Yeah. Okay, so actually, this alternative interpretation is actually my preferred interpretation because, it's using this interpretation, it's going to be much easier to talk about and define what is equilibrium. Okay, so we have talked about the rule of game and what is the situation we are looking at, right? I mean, yeah, the table summarizes everything about relevant things, right? Yeah. And some partition stuff, of course. Okay, so the next thing is that, in order to talk about anything about game, we have to talk about how to calculate expected payoff. Okay, so there are 3 players here: player theta C, player theta F, and player 2. Okay, so we have to calculate expected payoff for all these 3 players. Okay, so there are 3 players. So player theta C, player theta F, player 2. Actually, these are different types of player 1. Okay, so in game, all 3 of them have to choose their strategy. Okay. And they actually choose, regardless of what is true type of player 1, player 1 and player 2, they choose action simultaneously. Okay? So that means that, in order to describe what is strategy profile, we only have to describe what is probability of choosing each action for each player. Okay? And as before, I'm going to use notation sigma 2 to stand for player 2's strategy. So this is simply probability over 2 actions. Okay, either concert or football. And player 1s have 2 different customer types. So this is probability strategy of player 1 conditional on he is or she is type theta C. Okay? And this thing sigma 1 of theta F, this is strategy of player 1 conditional on my type is theta F. Okay? So here what's important here is that we allow 2 different types of player 1 play different strategies. Okay? This is kind of actually really natural, right? Concert type and football type, they have different preferences. Okay? So they must actually play, possibly in principle, they can play different strategies. Okay? So these are notations for this player, and this player, to stand for, to denote their strategy. Okay, then let's calculate what is player 1's payoff conditional on my type is theta C. So this is my, I'm gonna calculate player 1's payoff conditional on this guy is theta C. And of course, player 1 will play this strategy, right? And player 2 will play sigma 2. Is equals to, okay, so here I have this term here. So this is simply my strategy and my payoff of this guy when player 1's action is A1 and player 2's action is A2. For example, if player 1 goes to concert and player 2 also goes to concert, then, and my true type is theta F, that means that the payoff realized is this one, right? My type is theta F, and we go to the concert together. So player 1 of theta F type is that payoff is 1. Okay? But of course, there are 4 different possibilities, right? CC, CF, FC, and FF, right? And the probability that one outcome is realized is this thing. Okay, so this is probability that player 2 will choose A2, right? And this is probability that player 1 chooses A1 if this guy is theta N. Okay? So this is probability, let me write this way, probability of A1 and A2 and multiplied by payoff in that case. Okay? And if you sum all terms, all possible A and A2, across all possible A and A2, then that is my static payoff. Okay? So essentially what I do here is exactly the same thing we did for normal form game without any asymmetric information, right? So there is nothing new here actually. But I kind of, even if there is nothing new, I went through everything slowly, just to make sure you get familiar to all these notations. But once you get familiar to these notations, theta C and theta, I'm sorry, I have a mistake here. Yeah, it has to be theta C. Okay, and you can do exactly the same thing for the other type of player 1. So that's what you can see on the second line. And the third equation is something more complicated. So what is the third equation? The third equation is player 2's expected payoff. So player 2's expected payoff is this one if player 1 is sigma 1. I'm sorry, theta 1. So what is this one? What does it mean? This means player 2's expected payoff when player 2 plays sigma 2 and player 1 plays sigma 1, and because sigma 1 theta 1, where theta 1 can be either theta C or theta N, right? I mean, depending on what is real theta 1, either this is theta F or theta C, then anyway, so this is gonna be the player 1's strategy. And once you fix player 1's strategy and player 2's strategy, then you can calculate the expected payoff, right? But the thing is that theta 1 here, it is random variable in player 2's perspective. Player 2 does not really observe whether theta 1 is theta C or theta F, right? So theta 1 is random variable. Actually, theta 1 is theta F with probability 1/2, and theta 1 is equal to theta, the other state with probability 1/2. So anyway, this term here is random variable. So in order to compute the expected payoff, you actually have to have expectation operator here. Because theta 1 is random variable in player 2. Okay, so maybe it's kind of trivial thing, but I think it's helpful to notice that we don't really have this thing here. Why? Because player 2's payoff in all possible outcomes does not depend on player 1's time, right? So we don't really have to put this part inside the player 2's payoff function because it does not really depend on theta 1. So my payoff can be different only through the player 1's different strategy depending on his or her. Okay? Okay, then if you want to calculate this thing, there are two possible sigma 1, right? I'm sorry, theta 1. So, and this is the probability that I think here is another typo here. Here we have row we have to have row subscript 2 because we are talking about player 2's building. Anyway, they have common prior, but strictly speaking, we have to have row subscript 2. Okay, so with this probability, player 1 is C guy, right? Construct guy. And in that case, player 2's payoff is 1. Player 1 will play this strategy, right? So this is strategy of player 1 when this guy is C guy, C type, construct type. And then I'm gonna still play sigma 2. So this is my payoff when player 1's true type is theta C, and that happens with this probability. Plus, with this probability, the true state is the other one. And in that case, my payoff is equals to this. Okay? And of course, you can also, expand, open this black box, this term, expand this term, which is actually equal to the one in the bracket in the screen. Okay, any question? So, any question? Here, let me emphasize again. Here essentially there is nothing really new here, right? I mean, we have payoff functions and strategies, and expected payoff is simply calculated simply by adding up all possible payoffs, weighting, with using probabilities as weight for different possible situations, possible states. Okay, and basically that's it. Okay, I think I have to finish right now here. So okay, so this is the way we calculate expected payoff. So I'm gonna repeat the same calculation one more time next week. Okay, so then here is the key idea of what I actually would like to do eventually. So here we have to define what is the equilibrium concept, right? And in equilibrium, obviously everyone have to play their best responsibly. And here we have three players, technically. So there are player 1 and player 2, but technically player 1 can be either type C or type F. So technically speaking, there are three players, right? And if all of them choose their best response toward the other player's strategy, then we can say that that is equilibrium. And the basic idea and spirit is exactly the same as the notion of that equilibrium. And that's and that concept of equilibrium is something I will for Bayesian or Bayesian. And that's the equilibrium concept we're going to use to analyze Bayesian.